All right, so let me now introduce this idea of the exact discrete Hamiltonian. Okay, so let's call that HD plus exact. Depends on Q0, P1. Okay, and this is going to be the extremum over P at the final time H. So maybe let me just explicitly say it depends on H as well. Okay, so PH Q at H minus the integral from 0 to H of P Q dot minus H QP dt. Okay, and I'm extremizing over Q and P, which are twice differentiable curves from the interval 0 to H to T star Q, subject to the boundary conditions that Q at the initial time 0 is Q0 and P at time H is P1. Okay, so if you recall, it's like with the exact discrete Lagrangian, you could view this as a solution, basically Jacobi solution of a Hamilton-Jacobi equation, and there is an associated type 2 Hamilton-Jacobi equation to this, right? So this is associated with a type 2 sort of Hamilton-Jacobi equation, which I'll write as the following: ds2 q0p t dt is equal to h of ds2 dp comma p. All right, and then the idea is that you're solving for S2, which is the type 2 generating function, which maps Q0 and P0, if you will. It's like to some final momentum P at some time t. Okay, so you're looking for a generating function of this form, where you prescribe the initial position, you have the momentum at some later at time t. It's like, and then this is a time parameterized generating function of the flow map. Okay. All right. In any case, then the sort of the discrete Hamilton's equations, right? So then you have sort of discrete Hamilton's equations. Are given by let's say, well, let me write it as in terms of index k. So qk is equal to d2 hd plus qk minus 1 pk, and then pk is equal to d1 hd plus qk pk plus 1. Okay. So these are the discrete Hamilton's equations, and you can think of them as implicitly defining, so they implicitly sort of define, and then this goes from k equals to 1 to n minus 1. Actually, it goes from k equals to 0 to goes from k equals to 1 to n, and then this goes from k equals to 0 to n minus 1. So they implicitly define a map qk pk to qk plus 1 pk plus 1. Actually, maybe it's better to reindex this in the following way. exact. So you can write it this way. It's like, and then implicitly it finds this kind of map. Yeah, so if you know qk and pk, you can use the second equation to solve for pk plus 1. And once you know pk plus 1, it's like you can use this first equation to solve for qk plus 1, right? So, so that's sort of a discrete version of Hamilton's equations. And then that's just the exact discrete Hamiltonian, okay? And then, as was the case with it's like Lagrangian variational integrators, then you can imagine constructing computable discrete Hamiltonians by replacing this family of twice differentiable curves. It's like which mapped into T star Q by some finite dimensional analog or subspace. It's like, for example, the space of polynomials. And then by replacing the integral, it's like by some sort of quadrature approximation. So we'll talk a little bit about how you can go about doing that in a little bit. All right? So we'll stop for now.